Hi folks, I want to share a simple idea. The notion is, let's suppose you make a measurement of some kind, a voltage, a current, a light intensity, it could be anything. And the problem is that it's got some uncertainty associated with it, and you want to reduce the amount of uncertainty associated with a particular measurement. So a common approach that I'm sure you've used in the past is that you measure the thing a bunch of times, and then you calculate the average value of that measurement. And the idea is that, well, by taking an average of multiple measurements, clearly you're reducing the uncertainty associated with that measurement. But the question is, how much are you reducing the uncertainty? How much improvement do you get in the confidence you have in the value that you calculate from that mean relative to the confidence you would have if you just took a single measurement? And so that brings about the idea of the standard deviation of the mean. So I want to just illustrate that idea with some simple, sort of generative data generation experiments, Monte Carlo experiments, and see how that works. So what I've got here is a NumPy normal distribution. I want to take 100 measurements with a mean of 3.2. Standard deviation of 0.5. So we have some numbers that vary about a mean of 3.2 by, a half or 1 or something like that. And then we produce a kernel density probability distribution based on that 100 data points. And you can see that it looks sort of roughly normal-ish. And the mean is about 3.2. And you can see that most of the data is between 2.7 and 3.7, right? So that's about 70% of the data, I suppose, and 95% of the data is within plus or minus 1 of there, and so on. So that's looking okay. But the question is, what happens if I calculate the mean of these 100 data points that I've measured? And so to look into that, what I've done is write a little loop here that goes out and generates 100 random numbers, calculates the mean, and throws those into a list. So now I get a list of 100 samples of 100 means, each of which is produced by a collection of 100 random numbers with a mean of 3.2 and a standard deviation of 0.5. And what I want to do is look at what happens to the standard deviation of those means. So I'm now calculating a bunch of means, and I'm getting the standard deviation of those means. And what you find is that the standard deviation of the mean is about 10 times smaller than the original standard deviation of the population that I'm measuring. So by taking 100 of them and calculating the mean, I'm improving my standard deviation by a factor of 10. Now, and then here's the graph. There's the original distribution of numbers. Here's the distribution of the means. So the means are much, much more tightly focused on that region right around 3.2 plus or minus about 0.05, whereas the original distribution had a distribution with a standard deviation of about a half, so 10 times bigger. You're going to find that, and you can prove this, it's not that hard to prove, but the proof isn't terribly enlightening. It turns out that in general, when you make a mean of n measurements, the standard deviation of the mean goes down by a factor of the square root of n. So since in this case n was 100, square root of n is 10, so the standard deviation of the mean goes down by a factor of 10. And you can use that to actually decide how much data you need. If the standard deviation of your data set is plus or minus so much, and you want to make it 10 times smaller, you need 100 samples. If you want to make it 5 times smaller, you need 25 samples, and so on. So you need a number of samples, you need the square of the factor. So if you want to go down by a factor of 6, you need 36 samples, and so on. So you can generally see that that's the plan, and that's the way it works. So I'll post a link to this URL in the description of the video, but that's the basic idea. Hope that makes sense. If you have any questions, don't hesitate to ask.